last time, remember, we started talking about interval estimates, right? And we talked about, in particular, the interval estimate for a proportion. Yes, okay. In this section, we're going to start talking about how we construct an interval estimate for the mean. And there are two times or two conditions under which we do this. And I may have these kind of backwards as far as the sections go. But that's okay. We're going to do this one first. We're looking at when we construct an interval under these conditions. First of all, sigma is known. Okay, sigma is the what? Population standard deviation. Okay, so we know the population standard deviation, and well, first of all, we have a randomly selected sample. So just random sample, which we always do, or assume anyway. And the second condition is either the population is normally distributed or n is greater than 30. Okay, and just for reference in the textbook, yes, I am. Page 353. We'll come back to this page first. Like I said, I had them turned around. All right, when I do that, then I'm going to do a z interval for the mean. Okay, we talked about z intervals last time, right? And we also talked about how we get that on our calculator. So the formula is confidence interval for the mean is x bar plus or minus z alpha over 2 times sigma over the square root of n. Okay, and this is, again, when sigma is known. All right, we're going to have similar conditions when sigma is unknown. The only thing that's going to be different is that instead of doing a z interval, we're going to talk about a t interval, which we haven't looked at yet. So how does this work? We've got this example. It says an urban economist wishes to estimate the mean amount of time people spend traveling to work. He obtains a random sample of 50 individuals who are in the labor force and finds that the mean travel time is 24.2 minutes. Assuming that the population standard deviation of travel time is 18.5. That's the cue for me. Okay, because I need to know whether or not the standard deviation given to me is from a population or from a sample. But here, if it's from a population, it's going to say that clearly. Okay, population standard deviation. All right, so assuming the population standard deviation of travel time is 18.5 minutes, construct and interpret a 95% confidence interval for the mean travel time to work. Okay, so when I hear population standard deviation is known, then I know I'm going to do a z interval for the mean. That's my cue. Okay, and if we wanted to, we could, by hand, we set the formula for the confidence interval is x bar plus or minus z alpha over 2 times sigma over n. X bar in this particular problem is what? 24.2. Plus or minus, we've got a 95% confidence interval. What's the z value for that? .96. Very good. Okay, and our standard deviation, they told us, was 18.5. And the sample size in this case, I didn't stop and think about that. Okay, in order for me to do this, I really do need either to know that the population is normally distributed, it didn't say that, or that my sample size is greater than 30. Do I have that? Yes. Okay, I got a sample size of 50. Okay, so we could put it into our calculator. Okay, and we've got 24.2 minus 1.96 times 18.5 divided by square root 50. R. Delete. Okay, that gives the lower end, and if I do that again, except I'm going to add this time. Stop. All right, 29.32. So my interval, or my estimate for the population mean, would be 19.07 to 29.3. Okay. All right. How would we interpret this? Okay, this problem, what was it about? The amount of time people spend traveling to work. So our 95% confidence interval estimate for the mean time that people spend traveling to work is between 19 minutes and 29.3 minutes. Yes. Remember we talked about those common levels for of confidence, the 90, 95, and 99. Okay, so 1.96 corresponds to a 95% confidence interval when we're doing Z intervals. Okay, T intervals, altogether something different. Z intervals, this is how we do it. Okay, even better though, it gets better, like the infomercial, but there's more. We're going to go to stat, go over to test. We're doing a Z interval for the mean, so that's option number 7. Okay, and I tell it the information. There are two sides here. The first option is for data. If you, let's say we're doing your own study and you had not calculated the mean and standard deviation and all of that stuff, then you could put your data in a list and it would pull all that information for you. Okay? But for most of our problems, I'm going to give you the mean and standard deviation. So you want to arrow over to stats, hit enter, and then now you see where it tells you you need sigma, x bar, and n. Okay. Additionally, the calculator does a really good job of reminding you that if you're over here looking at Z interval, you need to know sigma. Okay. If you don't have sigma, then you don't need to be in this area. All right. So if what you have is a sample standard deviation, this is not the place for you. Okay. So then we just tell it what those values are. My standard deviation was 18.5. My sample mean is 24.2. And my sample size is 50. And level of confidence is 95%. And so we got the 19.07 to 29.33. So it's just a matter really of deciding what to do. And we decided to do a Z interval because, first of all, we knew the population standard deviation and we have a sample size that's more than 30. Okay? Well, you know what? Let me step back. Because in both the T interval and the Z interval, we're going to have these two requirements. You got to have a simple random sample, and either the population needs to be normally distributed or you got a large sample size, greater than 30. Okay, so that's really not a distinguishing feature. That just has to be, no matter what. But other than that, it's whether or not you know the population standard deviation or you just have a sample. Okay, so really, with Z, it's a population standard deviation. When we compare, we hadn't really talked about the T interval yet, but when we compare a T interval to a Z interval, T intervals tend to be a little wider. And so therefore it's going to make your interval wider. And it's appropriate for us to use that when we only have a sample standard deviation, because we're really not exactly certain about the spread of the data. Versus if I know sigma, then I already know what the spread of the data is. Okay? And so I don't need that extra room to be certain. Okay? So that's why we use a z interval here when we know sigma, and we'll use a t interval when we don't. Okay? Let's take a look at another one. After watching a drama that seemed to last a long time, a student wondered how long a typical drama lasted. She obtained a random sample of 30 dramas. Let's just say 31 to make this easy. All right, and found the mean length of these movies to be 138.3 minutes. Assume the population standard deviation length of a drama is 27.3 minutes. Construct a 99% confidence interval for the mean length of a drama. Okay. So again, what are we asked to find? We want to construct a what? Confidence interval. What kind of confidence interval? For mean. Okay. Last time we talked about proportions. Now we're talking about means. So I need to know whether or not I have sigma. Do I? Yes. It tells me that this is a population standard deviation. It's either going to have to say those very words, or it's going to say sigma equals. Okay? All right? Otherwise, if it just said standard deviation, you know, unless there was something to make me think it was from a population, I would assume that it was from a sample.
So wouldn't that be the same thing as sigma equals?
In this case, yeah. Those say the same thing. Versus a little bit later, we're going to talk about a sample standard deviation, which is represented by S. Remember? Okay, so we're going to do our confidence interval. And so we can just do it on our calculator. Okay, we go to Stat, Test, Option 7. Okay, my population standard deviation is what? Okay, 27.3. My mean is 138.3. Very good. My sample size, I made it 31. A lot of textbooks, I'm not sure why our author says greater than 30. Most textbooks would say greater than or equal to. But since we're going with his book, we're going to do it his way. So N is 31, and the level of confidence is 99%. So 0.99. Okay, we calculate, and we get 125.67 to 150.93. What did I say? 150.93. Okay, good. All right. So, what were we looking at? We're estimating the mean length of these dramas. And so we believe that it's between 125.7 to 150 minutes. Okay, questions about that? Not bad, right? Okay, most of this we've already talked about from last time. The margin of error. Okay, we talked about margin of error, and we really don't need to talk about it actually. Margin of error versus sample size. We said that as sample size increases, what happens to margin of error? Decreases. Okay, very good. As level of confidence increases, what does margin of error do? It increases, okay? So we already kind of know the relationship between those things. So we have a formula that allows us for the mean to determine the minimum sample size. Okay. So our formula for minimum sample size is N equals Z alpha over 2 times sigma over E squared. Okay, this allows us to select a sample size that will let us have the minimum, or rather the required margin of error and level of confidence. Okay, so let's see what these little problems are going to say. A wildlife study is designed to find the mean weight of salmon caught by an Alaskan fishing company. As a preliminary study, a random sample of 50 freshly caught salmon is weighed. The sample standard deviation of the weights of these fish is 2.15 pounds. How large a sample? Different question now. How large a sample should be taken to be 99% confident that the sample mean is within 0.2 pounds of the true mean weight? Okay, so they're asking me to find the what? Sample size. And we just said that that's N equals Z alpha over 2 times sigma over E squared. Okay, we're still doing this with a certain level of confidence. So even though our calculator does a lot for us, these minimum sample size formula, it does not do. So you got to remember how to do those. Since we're doing 99% confidence, what's Z? .575. Okay, the standard deviation, and with this, it doesn't matter where it comes from. That's not an issue. Okay, so our standard deviation is 2.15. Yes? And our margin of error is 0.2. Okay, so all that in, we're going to square it. 2.575 times 2.15 divided by 0.2. And then I'm going to square that. Excuse me, 766.25. We're going to call that what? $7.67. We always round up. Okay, we can't sample a fraction of a fish, and we gotta go with one number or the other. If we round down, then our margin of error goes up. So we have to round up. Okay, always round up. So we would try to get 767 fish. Okay, questions about that? I know. What is that? Okay. It's like a stink bug. Y'all gonna make me take one. Is it really gonna stink? Okay, this is all on the recording. Okay. I don't know. Okay. I know, edit. The Adventures of Live Class. Edit. Okay. Alrighty. She'll be back in a second. Let's cheer for her. Yay! Alright. A certain company makes light fixtures on an assembly line. An efficiency expert wants to determine the mean time it takes an employee to assemble the switch on one of these fixtures. A preliminary study used a random sample of 45 observations and found that the sample standard deviation was 78 seconds. How many more observations, this one's a little tricky, are necessary for the efficiency expert to be 95% sure that the point estimate of the mean will be off from the true mean by at most 15 seconds. I don't know what these strange boxes are that keep showing up. Okay. But anyway, what's that? Nope, you got to know the formula. Okay? Got to know the formula for these. Okay? So again, we're looking for the what? sample size. So we get n equals z alpha over 2 times sigma over E squared. All right, the level of confidence is 95%, so that's what? 1.96. Okay, our standard deviation, we're going to use 78. And our margin of error is what? 15. Okay. So all that and square it. And what do you get? 103.87. Okay, so we would call that 104. Okay, 104. But the question is a little tricky. It says how many more? So we would say what? 104 minus 45, 59. 59 more. Okay, because it said that they used 45 observations to come up with the standard deviation that we used. Okay, so how many more? That data is still good. Okay? All right? Yes. Okay. Okay, very good. All right. So now we need to talk a little bit about the t-distribution. And again, we've got the same conditions. We've got a simple random sample. We've got either a normal distribution or n is greater than 30. And most importantly, sigma is unknown. And so we're going to use a t-distribution, but it looks almost exactly the same. We have x bar plus or minus t alpha over 2 times s over the square root of n. Okay? Has to be s, because if I know sigma, I'd be doing what kind of interval? A z interval. A z interval. Okay, but since we know, since we don't know sigma, then we can do this t interval. Okay, so here's a t-table. And the t-distribution, like I said, is very similar to a z-distribution. It's approximately normal, but it has just a little more spread. Associated with the t-distribution is the idea of degrees of freedom. Okay, before we can look at this table and understand it, we need to know about degrees of freedom. For a mean, the degrees of freedom is 1 less than the sample size. Okay, 1 less than the sample size, or just n minus 1. All right? This is the t-distribution. And this is really important if you're using the table. What was that? For the mean, the degrees of freedom is n minus 1. N minus 1. Okay? So when you look at a t-distribution table, then on the leftmost column, you see that we have degrees of freedom over here. And then across the top, we've got the area in the tail. Okay? And so let's say we've got a sample. No, I knew that was going to happen. Okay, let's say we got a sample size of 16. And if we had a sample size of 16, we would have to know that our population is normally distributed. And let's say we're interested in a 90% confidence interval. All right. Then if I've got a 90% confidence interval, which is here in the middle, then how much area do I have in the tails? 0.05, okay? And my degrees of freedom would be 15, one less than the sample size. Okay, so I would come down to 15, and then I would go beneath the heading for 0.05 right here in the tail. And so my t value would be 1.753. Okay, let's do inverse t. The area to the left is 0.05. Our degrees of freedom is 15. Let's see if that works. Hold on. Yay. Yes, that's right. One less than the sample size. Okay, so inverse t, if you don't want to use the table, inverse t, our syntax is area to the left. We had 0.05 to the left, right? And then our degrees of freedom was 15, and so we got 1.753 just like we do here in the table. Yes, ma'am. That was on the distribution menu. So second, vars, and number 4 was inverse t. Oh, that's going to be the slight difference right there. Yeah, so you'll have to use the table if you don't have the 84. That's probably the one thing I've seen that's different between the 83 and the 84. Right. It's the same thing, you know. It's more compared to, it's kind of backwards, because remember in the Z table, all of these numbers in the center were areas. Remember that? But in a T table, all of these are more like Z scores. Yeah, so the table is backwards. And that's why we're just using this inverse T. Okay? So yeah. I chose number 4, inverse T. Number 4, yes. I did, and that makes sense because if the area to the left is 0.05, it would have to be over here on the left side. I would go with the negative. Okay, the way this table was set up, they don't have the plus and minus values. In fact, T tables usually don't. You have to depend on the way that the picture looks. And if we've got 0 here in the middle, then we've got negative values over on this end and positive values on that end. And remember, it's still symmetric, but that's a very good point. The value is negative 1.753 if you're using the table and the calculator. Okay, so let's see if we can apply this for a little problem. Okay, we got this problem regarding tensile strength. Tensile strength is the amount of stress a material can withstand before it breaks. Researchers wanted to determine the tensile strength of a resin cement used in bonding crowns to teeth. The researchers bonded crowns to 72 extracted teeth. Using a tensile resistance test, they found the mean tensile strength of the resin cement to be 242.2 newtons with a standard deviation of 70.6 newtons. Based on this information, construct a 90% confidence interval for the mean tensile strength of the resin cement. Okay, and then we have this other problem that kind of ran into it. All right, so scratch this out for now. All right, so we're doing a confidence interval for the mean, right? And so we need to ask ourselves, do we know sigma? Do we? Okay. Does that come from a population? No. Okay, so we don't know sigma. Remember, we'll always be given a standard deviation. The question is, does it come from a population or from a sample? And in this case, this standard deviation is based on the sample of the 72 extracted teeth. Okay, so we've got S equals what? 70.6 newtons. Okay. Do we have conditions met along either a normal distribution or a sample size that's greater than 30? Yes. Okay. N in this case is 72. So we can do our confidence interval on the calculator. And I think you can do this still on the 83 as well as the 84. So we're going to go to stat, test, and then we want to do a t interval, which I believe is going to be option number 8. Okay. We got a happy TI-83 user, right? The sample mean in this case is what? The sample mean was 242.2. And our sample standard deviation, notice here on T interval it says, hey, you need a sample standard deviation, not a population. So 70.6. Okay, my sample size, 72. My level of confidence was 90.9. Okay, so our confidence interval is 228.33 to 256.07. Okay. Questions about that? Yes. That's right.
See, I see what you said about standard deviation. I see the N,
Mm-hmm.
72 standard deviation, and the 9.
Mm-hmm. It'll always be the same way on the calculator. So, it asks us for the sample mean, X bar, that's going to be first. Then for the T interval, it asks us for the sample standard deviation. If it was a Z interval, we'd be putting in population standard deviation there. We get the sample size and then the level of confidence as a decimal.
Well, all the have the numbers there, or do you
No. The only time you would have to figure it out is if you had just a set of data. And then you got to go and find the mean and standard deviation. Or if you had it in a list, then the calculator would compute it for you if you did the data option. But as far as the test goes, those numbers will be there. Okay. It's only if you're trying to find that t value. And that would be on the table or on the calculator. So if we did inverse t, the syntax for that was area to the left and degrees of freedom. Okay, area to the left and degrees of freedom. All right. Okay, other questions? Okay, well, let's try one more. Okay, for a simple random sample of 40 2007 Ford Mustangs, the mean gas mileage was 20 miles per gallon with a standard deviation of 1.5 miles per gallon. Construct and interpret the 95% confidence interval for the mean gas mileage of similar 2007 Ford Mustangs. Okay, I want you to try this on your own. Okay, so in this problem, again, we want to construct the 95% confidence interval for a mean. And so the first thing I want to know is where the standard deviation come from. Comes from what? Looks like it comes from the sample. Okay, I'm going to make sure that my sample, or rather that I meet the other conditions. And in this case, which condition do we meet? Okay, we got more than 30. All right, so I'm going to do a t interval. So on my calculator, I'm going to go to stat test number 8. Okay, the sample mean in this case was 20. Oh, I messed up something. Hold on. Test number 8. Excuse me. My sample standard deviation is 1.5. Okay, very good. And our size here, we really do put in sample size. We don't worry about degrees of freedom. Put in the sample size, which was 40. And our level of confidence is 95%, so 0.95. And it handles everything else for us. Okay, we're going to hit calculate, enter. So our confidence interval for the mean gas mileage for similar 2007 Mustangs would be 19.5 miles per gallon to 20.5 miles per gallon. Okay, questions about that? All right, very good.